Okay, all right. So it's my great pleasure. So welcome everyone. So it's my great pleasure to introduce Professor Swagatam Das. So Professor Swagatam Das is a professor at ISI Kolkata. He earned his B, MA, and PhD degrees from Jadavpur University. Formerly deputy director of TCG CREST. His research spans deep learning and non-convex optimization with over 400 publications. He co-founded Swarm and Evolutionary Computation and SARS as an associate editor for prestigious journals with 32,000 plus Google Scholar citations and an incidence of 84. So he is renowned internationally, participating in top conferences like NeurIPS and receiving accolades such as 2012 Young Engineer Award and 2015 Thomson Reuters Research Excellence India Citation Award. And he was also my undergrad advisor at Jadavpur, and I wrote my first journal paper with him, third year undergrad. So welcome, Professor Swagatam Das, and
that's the connection.
Okay, so over to you.
Very good morning to all of you. Unlike most of you, I was not sure about the level of audience here. So this talk will be partially a Colossian type talk with some takeaway for many theorists here. And if you look at this opening slide, I hope it is visible over Zoom also. This diagram was made by Jadavpur when I prompted it to use this title and make me a nice background for the slide. So it made something like this.
Thank you for creating.
And these sort of things are well covered in everywhere. We are going to see some very important ethical perspectives of LLMs. I don't know how many of you are regularly using LLMs. Do any of you use ChatGPT, GPT-4, Jadavpur, or similar like Llama or Palm 2 kind of stuff? Not much, right? You use, right? So the usage itself should make you very much experienced about their certain good and bad aspects. So I will start with very basics and delve deeper as it is applicable. Let's just minimize this. The biggest selling point of deep learning, which these two words became very famous since 2012, was that they do not require human intervened feature engineering as is required in the traditional machine learning cycle. They are context sensitive feature extraction followed by classifier. That's the biggest selling point. When I go to a bank and ask for a loan, if I opens up in my name, I try to become specified in terms of my credit rating, civil score, etc. Fixed deposit. I become a piece of data. If I go to a blood bank and try to become a potential blood donor, they start specifying me in terms of my thalassemia, proneness, my blood glucose, blood sugar, and so on. Same person, completely different set of features. So you change the context, and the numbers that specify you, that abstractly represent you to a digital computing system also change. Deep neural networks sense that context from the same output cost function and then go on learning a very clever representation of the object in terms of the most informative, discriminative set of features, which are of course much less in number than the total measured set of features to specify each object. That is supposed to be their biggest selling point. And you can see this very earlier first generation deep neural network, which is basically a Lenet finds, and these are handwritten digits. These convolutional layers are learning the proper representation of this digit in terms of not pixel level features, but okay, there is a vertical rod, there is a circle and a vertical rod. If the circle is on the top side, then it's 9, downside it might be 6.
How do you draw this conclusion? Can you actually look at the first layer and see that that's what it's done?
Yeah, we can actually nowadays probe these layers and learn what are the intermediate representation features. Okay. And at the output, so this is the main classifier. This dense layer is the main classifier. These are the representation learners. And at the output, we just give you a probability of its being.
Sorry, what are you saying in layer 3 and 4? What are they learning now? Layer 3 and dense layer 1?
Actually, these maps, they are being summarized in terms of certain numbers sitting together. These are encoded feature logics, like there is a horizontal dot and there is a vertical dot. This is a schematic picture. You really don't see the numbers, but in actual case, you have a lot of numbers coming together which summarize these things. And the summary is like if you have a 28 cross 28 Amidst image which has 784 pixels, the summary will be in 10 or 12 numbers, which will tell you if there is a slant line, if there is a circle, if there are two circles, which makes it 8, and so on. And similarly, you can have this sort of stuff also. This is a full-grown convolutional neural network. So you have this input image, you extract small patches from the image, and then you operate on the higher abstract level features encoded in these patches, like the eyebrow constriction, the nose, the wrinkles on the cheeks, and so on. And based on such higher level features, you finally, in these fully connected layers, you classify. First, you represent the image in terms of such higher level features. Higher level means closer to human interpretation. Then you classify them to belong to one of these 7 possible emotional states that is being shown here.
This is what the network is doing. Is there a clear guideline as to what should the first layer be made of? Basically, you're constructed. You try to
Yeah, that's a very good question.
Yeah.
So the network, these sort of networks, what you can see here, are constructed based on experience and trial and error of the practitioners. There is no clear guideline.
There's no wisdom that's come out.
No, the wisdom that comes out is in terms of what kind of, had it been a medical image. Now people try to understand how it demarcates between two labels. Okay, we call it explainability, and when explainability comes, in many cases it matches with the doctor's clinical eye. Okay, especially that is seen in this sort of cancer detection programs, which are now dominating the entire medical imaging field. But when we, now there are some guidelines that, okay, your first convolutional layer size, there is some convolution arithmetic coming from signal processing, which gives you these numbers.
Actually, we're using convolutional layer early on. That's also some, it's something after experiments, people have found that convolution is a good layer to that. Is that right?
You will affect its fairness.
No, I'm just saying, why not just have a regular layer, like convolutional layer?
Oh, okay. So the regular layer, had it been a fully connected regular layer, it would require 10 times as much trainable parameters as the convolutional layer. Convolutional neural networks are compacting the whole neural architecture because they are working on patches.
Right.
Okay. And we are assuming that the pixels bear a great deal of redundancy, which is always there. So we look at the patches and we try to summarize the patches. These convolutional layers, you can say it's as if it is dragging a small submatrix on the entire image. And the submatrix is looking for certain very important feature. Is there, had it been demarcating between cars versus non-cars, it would look for whether there is an engine pipe, there is a handle, there is a steering, and so on. So such feature extractors are not looking at the image pixel by pixel, but looking at the image on patch by patch basis, and then summarizing them, then they are finally, downsampling them through this pooling process, and that workflow continues until the image, the full image, which maybe now megapixel cameras are so common. So you may have a 1 million pixel image. We are not going to use all these 1 million pixels together. We are going to summarize it into maybe 500 numbers, which would actually tell us if the eyebrows are constricted, if this forehead is having shrinks, and so on, based on which based on the training set.
Images which have continuity around them, convolutional layers are good to summarize earlier. That's a good idea.
Yes. Convolution is nothing new. Convolution has been there for so many years.
It's all been replaced by something else now.
Now, the new idea is something like this. The kernels of the convolution are being learned. These are learnable kernels, and they are being learned based on the same cost function, based on which the classification weights are also learned. So you have a single cost function based on which you sense the context of your classification, card versus non-card, or bird versus non-bird. Should I look for feathers or should I look for engine pipe? That context is sensed from here, and then all the convolution kernels are modified.
So,
in every
so any filter that is used on a picture, let's say, make it blur or something, that is also convolution.
That is also convolution, special convolution, but that is handcrafted convolution.
Yeah,
and this is a learnable convolution.
Yeah.
Exactly, that makes the difference. Good. Now, there are two deep inference models, as in regular machine learning. One is this discriminative or predictive model, where we represent data items as dots in some abstract feature space, and we are very happy to learn this Lakshman Rekha or decision boundary between two groups of dots. This is the usual discriminative or predictive models. Then there comes the generative deep inference models, on which the entire generative AI, LLM, all these industries are standing. Here we are very much interested to estimate the underlying spatial probability distribution in some abstract feature space, from which these data items might have been sampled. It's an age-old problem in statistics. All of you know, I give you 10 random numbers and ask you, what is the Gaussian distribution from which they are most likely to be sampled? You will attack it with MNE or MAP or similar kind of estimators. But instead of 10 scalar numbers, what if I give you 70,000 images, each image 100 by 100? So 10,000 pixel images and 70,000 such images. And then I ask you, these images might be the head and shoulder image of cats. I ask you, now you estimate the underlying multivariate distribution from which the cat images might have been sampled. In face of such high dimensionality, most of these statistical estimation techniques lose their consistency, they cannot stand. And there comes the neural network based heuristics. Essentially, the neural network learns to, and like all numerical techniques, what they do is they learn how to, modify a very simple distribution, which would be a uniform distribution or a single pick Gaussian distribution, into a very distorted multimodal distribution that will closely mimic the data generating distribution of these images. This is the backbone of all generative models, right?
So,
And
so if I looked at these images, I have millions of them. I fit a multivariate Gaussian distribution. I do some kind of best fit and I generate samples from it. That would be much worse than what this is doing.
yes,
Right.
that is a proven fact.
That's cool.
Yeah, that's right. I think very recently, one of the ex-students of ISI, Gashu and Emmanuel Candace, they published a PNAS article on this, how this ML is not going to help at extremely high dimensionality. So you can see,
and this is much, much better.
This is much, much better. You can see, you can always look at neural network as a function. It has some input and some output. Now we say the input could be, nowadays, gone are the days when the input would have been just 4-dimensional vectors of iris flower 4 measurements and the output is 1 class level. Now we say, okay, the input could be a 1 megapixel camera image and the output could be 10 words which describe what happens inside the image. And this is happening. So you have a programmable interface or a function which will convert the image into words. Generative model similarly transforms one distribution into another distribution. And the output distribution is guided by the example samples for that target distribution which we want to model. This is exactly one of the most interesting generative models called GAN, or Generative Adversarial Network, which you can see. If you look at the initial approaches, you see it starts with complete noise. Then it learns how to arrange these noisy pixels to form this sort of meaningful handwritten digits, which were not there in the example set being shown. So generative model doesn't clone. Okay, you show it some set of examples. It tries to manufacture similar images which are not there in your example set, but from the same genre. Am I clear? Okay. So this is it. And now this is the progress of GAN generated images over time. In 2014, when GAN came into market, we didn't have NVIDIA GPU series 3090, 4090, 100 and so on. Now with all those computational backup, this lady, this man, you can see the wrinkles, gray hairs, the lady doesn't exist. These pictures were never shot on camera. These were actually prepared by GenAI. Okay? And this trend goes, this was just the beginning. StyleGAN came into market in 2018. Next question was, can we translate the generation process between two completely different, categories of images? Let's say I would like to, okay. Yeah. So translation means multimodal data domains can be make translation. And they are decoding. So the expression of this person has been now translated into all these lanes. This old stare of the cat has been translated into dogs and so on. So you have two completely decorrelated image domains, and we call it image-to-image translation or eye-to-eye. And there are lots of very interesting works going on in this side. Sometimes this is just a video to give you a feel of how it actually happens. So you can see how Dave Patel's face is changing according to these different input source images, and Dave Patel is the target. These are hugely used in the fashion industry. We work closely with Myntra and Nykaa, where they do all this sort of stuff to create virtual try-on, to create special effects in their advertisements and so on. And this trend started from the ICCB 2017 paper that's called Image-to-Image Translation and Style Transfer, where you can actually translate the style of one image into another. For example, the horse has become the zebra here. Or you can mix up the features of two games like Fortnite and PUBG, you can mix and create something like this. And now the difference is you can tell, okay, these were there. These attempts were there for last 20 years in the computer vision community, but they necessitate separate studio, very costly lighting conditions, very costly set of cameras. Now you can do it on your handheld device because the neural network has made this very easy to do. Okay, this sort of image-to-image translation. The most interesting application comes in the form of
So can you describe exactly what's going on when we change horse into zebra in terms of the neural network, how we taking the
there are two, yes, I am skipping those details because I want to go to large language models, but there are two GANs. One GAN is converting from domain A to domain B, and the other GAN is converting it back. So it learns a full circular way between the two cross conversions, and then there is a cycle consistency loss, which measures the difference between the content of the two images when they are translated in the same domain and tries to minimize. That's how the style of, ultimately all the losses of GANs like networks are in terms of divergence measures. Finally, the theory of GAN has proceeded to a large extent. In 2020, there is a very nice paper in Annals of Statistics. You can go through it. It's called Some Theoretical Properties of GAN, which shows that GAN finally boils down to minimizing some form of divergence measure, which could be simply Jensen's divergence, Jensen-Shannon divergence, or KL, between two distributions. One of the distribution is not known and one is transformed from simple Gaussian. So something like that is happening. So one particular application is in class imbalance learning. In every rare event detection scenario, whether you have cancer or not, whether there is a credit card fraud or not, whether a cyclone will happen or not, in all these scenarios, the target class is extremely small. And because rare events happen at a much lower rate than the benign things happening around us, and that's good. So this is just one example of the work where you have this sort of class distribution, where this is the majority class and this is the minority class. And the minority class has very few points here. So the usual classifiers become biased towards the minority class. This is the decision boundary of a normal simple neural network, this boundary. Now, if you add a convex generator and a classifier, that also creates an adversarial training training architecture. Adversarial training means the convex generator is supposed to fabricate such samples which would be very tough to classify by the classifier. Usually such samples are near the twilight zone between the two classes. So the convex generator creates these green samples over here, and the decision boundary changes. Here the problem is you are misclassifying a lot of samples from the majority class. It's like you are testing for cancer, and a person who is benign, you are also telling you have cancer, start chemotherapy, which could be equally dangerous. So this work actually comes up with a three-player game. By the way, GAN, I should have told you, GAN uses two neural networks. One is discriminator and one is generator. The generator creates images from a noise distribution. The discriminator is like a critic. It provides feedback on the quality of the images by comparing it with the real-world samples. And we say these two neural architectures are playing a two-player zero-sum game with each other. They should eventually reach a Nash equilibrium, which, if it is reached, then it's very good actually. And the process minimizes some form of divergence. Here, this work is basically a three-player game where we have convex generator, classifier, and discriminator, creating this sort of, finally, then we call it gamma, because the discriminator is basically spreading these green dots like this and creating a nice distribution, and we have this sort of nice decision boundary. These are some images which are, this problem is for image classification. So these are some example images created by gamma-2-pix where these green dots are being converted into the real images from the minority class. Okay, so four prominent paradigms for deep generative models for image data up to now, which we have seen. One is GAN, which uses adversarial training, like we have a discriminator, we have a generator. The generator tries to adversarially perturb or fool the discriminator by making synthetic samples. The discriminator tries to catch up the generator by giving feedback. Then we have VA, variational autoencoders, which uses the variational lower bound maximization through an encoder-decoder architecture. Then we have invertible transformation of distributions of the flow-based models. And the latest ones on which Jadavpur and every modern image to text to image systems are standing are called diffusion models. Diffusion model operates on a series of stochastic differential equations, and now mathematical community is taking a keen interest of it. The basic fact is you have training images, you start adding noise onto the training images until they become completely noisy like this. This is the reverse flow, the forward flow is like this. First, you will have multitude of training images. You will take an image, you will go on adding noise onto it until it looks completely noisy. Then you will remove the noise by using a neural denoiser until you get back the original image. You do this forward-backward mapping on all training images. Now you take complete noise image like this, feed it to the reverse path. When the noise will be eliminated, that complete noise image is just noise. It was not made by adding noise to some existing image. Now when the noise is completely eliminated, this image will become a new, this sort of image of the same genre, but not a cartoon. That is a generation by diffusion model.
So how do you put context into this feature?
There are various sideways perturbation schemes by which you can add conditionality, like generate people's image with specs.
So can you compare and contrast these techniques? Which one is better?
Diffusion is the best now, but nothing comes in machine learning without a cost. We call it no free lunch. Diffusion is extremely computationally heavy. GAN is very light compared to diffusion. So when we do not have A100 stacks to be available, we cannot actually simulate diffusion model. So this process has multitude of states and many intermediate neural denoisers.
So like for every backward transition, you need a neural network.
Yeah, that's right. That's right.
So that's how
That makes it a stack and very computationally very heavy. Okay.
So then that's the mathematical challenge to speed this up. That's probably a problem people think about.
Yeah, the most important mathematical challenge I was discussing with Abhishek also is, first of all, neural networks, whatever they are doing around the world, you can see the effect. Their architectures are quite heuristic. We have to do lots of engineering to understand how many hidden layers are optimal, how many nodes per hidden layer. It's convolutional. What should be the size of the convolutional kernel? 3 cross 3, 5 cross 5, what is optimal? Then, sample complexity is the major bottleneck. First, very interesting thing is, on the contrary of statistical learning theory, which says simpler models are always better. You have to hit the Occam's razor and so on. Contrary to that belief, neural networks are heavily parameterized. Still, they do not overfit. They do very nice classification. In fact, face recognition achieves 100% classification with convolutional nets. Whereas the best known before 2012, the best known classifiers were used to be random forest. Random forest accuracy was 80%, 80, bare minimal of 80, bare maximum of 81%, 82%. That's all. You get my point. Why over-parameterized models do not overfit? This is the mystery. Now people try to solve it, especially the Bartlett team, Peter Bartlett and their Martin Wainwright, they try to solve it using some concept called benign overfitting, but that is also not completely free of assumptions. There are a lot of, you start doing theory, you have to do a lot of assumptions. The second question is sample complexity, which is always the biggest problem of generalizability theory. How many training samples are good? Because in modern days world, especially coming to numerical imaging, labeled data is the biggest bottleneck. We don't have human experts who will label thousands and thousands of images for us. So how many sample trainings per images are optimal to get the test error below certain threshold, certain limit? This is called sample complexity. Sample complexity bounds some, attempts have been there, but all these attempts come with many assumptions, some of which are not enough practical. Do you get my point? And when the theorists make impractical assumptions, it's a very nice paper, but not much useful. That's where we lack some communication with them. But there are a lot of things to do in this side also. Okay, so deep generative models have been used to generate synthetic data, as I said, all these things. And now the entire world is being taken by the storm with the advent of large language models. Large language models, they are large-scale neural networks which use, you can call them abstract execution machines, which use natural language as an interface. So you given an input prompt means a question, an instruction from the user. It tries to capture the user's intention and produces an output answer in the form of the text string presented to the user. And computers do not understand language. Computers understand nothing beyond numbers. All of you know that. So the way some phrase of a language we organically understand, okay, some nice paneer butter masala, the way these phrase creates some image in our head or excites our salivary glands, is not the way the computer understands it. So how the computer understands it was hinted long back by John Fark, who was a famous linguist. You shall know a word by the company that it gives. So the computer sees for each keyword, what are the other words it is sitting with? What is the compositionality of this word with many other words in the closer vicinity? And what is the frequency? How many times the word red sits with a fire truck, then red sits with an idea, okay, or red sits with riding hood, something like that. So based on that association, it forms the meaning. And okay, so first of all, what is a language model? Language uses a finite number of symbols for tokens. We can assume a finite token set TOK of size k. Tokens may be letters, words, sounds, syllables. GPT that we are using, Chat GPT and other GPTs, they use sequence of letters, on average 1.5 tokens per English word. So we assume that is the average length. And we can treat the language as a stochastic process.
How many tokens does GPT use currently?
How many?
Tokens.
So this is just, if you go to letter-wise tokens, it uses on average 1.5 tokens per English.
No, but it must be well known, right, that GPT-4 uses this many tokens.
That is GPT-4's maximum number of tokens it can use per word. This is the average on all English words. Okay.
So you said the finite token set K.
Yeah, but it's of the order of, I think, 10,000.
This is, yeah, that's right.
So,
We assume a finite token set. That finite token set is very huge. There are specifications for different language models. Okay.
So it's 1,000, it's not billion.
It's not billion. The number of parameters is billion. Billion token is not possible in English, actually. So, and usually the models are autoregressive. Usual language models are autoregressive, meaning that they will predict They have a huge vocabulary. They start generating a line of text. They will predict the next word. They will assign probability to all the words in their vocabulary. And the most probable word they will pick and put in that blank to complete the text. That's how they operate. It's the usual language model. And with the large language models, now we are moving towards what we call artificial general intelligence. This is a little bit, I'll very quickly skip. Traditional programming, you know, the very smart human being will code certain set of rules, and then input comes, and then I just match with these if clauses, whether they're matching with the input, and if they're matching, then it's a cat. Wave of neural network from 2012. Now we have a machine learning system. We are going to show it 1,000 cat images and 1,000 dog images. Based on the 1,000 cat images, the neural network will learn the intricate differences between these two categories. A new cat image being shown, it will say it's a cat. Fine. Coming to generative language models like Lambda, Palm, GPT, it's like you are a very good professor, so you take your student to a library. You don't spoon feed the student. You don't show him lots of worked out examples. You take him to the library and say, here are the books on mammals, cats, dogs, reptiles, go and read them. Then come back to me and ask the questions. So the student does that, comes back. It's same as the training of LLMs. LLMs are actually trained on the huge internet-based repository of text in an unsupervised manner. After they get such training, when they come back, they have cats and millions of other concepts. So when you ask something to it, they can answer in a very nice way. Big, nice, concrete answers. This is called, and this is much like picking up the general intelligence. Large language models, therefore, are general purpose machine learning entities which can interact with you, pretending that it knows the syntax and semantics of a language, pretending. And they can be pre-trained and fine-tuned for specific purposes. What do pre-training and fine-tuning means? You think of training a dog. First, you teach it some basic postures like sit, come down, stay, which makes it a good canine citizen, right? But if you wish your dog to become a police dog or a hunting dog or a guide dog, sniffer dog, then you have to give it some more training on the basic postures. Same is true for large language models. Initially, they are trained, these neural networks are trained for very common NLP tasks like text classification, question answering, document summarization, etc. When they're trained on this plethora of very common NLP tasks, we call them foundation models. Like the OpenAI has its own foundation model based on which you can see all these GPT interfaces, right? Once it gets hold of this, now this foundation model could be pre-trained, could be fine-tuned for doing very specific tasks in different domains. You can use it for retail, finance, entertainment with relatively small size of data, with the use of in-context learning or ICL, with the use of prompting, React or RAG kind of prompting, and so on. And then in 2023, India has seen 150 plus startups opening up on LLMs. These 150 startups, most of the cases the IITians opened them, they are all based on this fine-tuning of foundation models, which is actually done by, which is under the control of OpenAI. So same ideas this way apply to LLMs. And therefore, once again, LLM is like a super smart computer program that has been trained on a huge amount of data and text and image and speech and whatnot. It's designed to understand and generate human-like language. You can think it as a virtual assistant that can read, write, and comprehend text just like you. And this is an example of fine-tuning. This is MedPalm2. You feed it with this sort of an image, like an X-ray image, and it writes down the findings, writes down a pathological lab expert's report below it. If it finds some anomalies, it can tell you, and so on. So MedPalm2 is coming from Palm2, which is actually fine-tuned only on the medical data. Okay. Now, most of the medical automated diagnostic systems use MedPalm2 as their interface. That's how they have gathered a huge, market. Similarly, Llama from Meta and so. So at the heart of LLM, now let's become a little technical before I go to the last part, ethical part. At the heart of LLM, there is a transformer model. What is this transformer model? There is an encoder and there is a decoder. The encoder is a neural transformer, which is taking this input, text input, converting these text inputs into numbers, squeezing these numbers into small size vectors. These vectors reside in a very mysterious latent space. And in this from this very mysterious latent space, the vectors are sampled by the decoder. And the decoder does a reverse process, creating a line of text. If we look at NMT, the neural machine translator, while this space is very mysterious and very strangely characterized because the same word, ma, amma, mother, all these words in different languages mean the same entity. So geometrically, all such numerical embeddings and numbers are same in all languages, right? So geometrically, the encoded vectors should lie in the very close vicinity if they mean the same thing. So semantics has a very important relationship with this mapping to this intermediate latent space. The latent space is very poorly theoretically characterized. People do not understand. Where a lot of things can be done and is being done, tried to be done. The basic fact, so this entire architecture, transformer with multi-head and self-attention, came only in 2017 in a very nice NeurIPS paper called Attention is All You Need. And attention, along with the self-attention mechanism is just about finding the relation between two words in a sentence, which might be separated by other less related, less required words. So it's like when you are an adult human being, when you read a line, you don't read it by every article, every preposition, every conjunction. Your mind picks up 3-4 major keywords and the meaning of the line is formed in your head. Not only that, when you are reading continuously, the meaning of this line and the meaning one paragraph below what you have read, those get automatically correlated. That process is actually imitated in the self-attention method.
So one question for you. Now, LLM is basically one big transformer or it has many transformers?
Very good question. LLM is actually, if you look at LLMs, they are multiple stacked transformers, but this part is hidden. GPT stands for Generative Pre-trained Transformer, where we only have the decoder. The language representation part, how they are learning from huge text corpora on the way, and how they are summarizing that, this part is not open to public. Public can pre-train, fine-tune only the decoder part. So not open because Facebook, Meta and Google, and of course OpenAI, they have all kept this under their secret.
So if we had to make a LLM, will we use one big transformer or will we use many?
We are using the decoder of one big transformer.
If you build a LLM from scratch.
If you build an LLM from scratch, nothing can be. Bharat GPT is trying to do that in conjunction with Google and this Government of India, IIT Bombay, Pushpalda is there. But the problem is creating an LLM from scratch, which would work with 22 plus regional languages, requires huge amount of computing, huge money. Where we are left.
So right now you don't know if they're going to be using one transformer or many or what the are.
It's always better to use multiple stack transforms together and then somehow combining their outputs.
Basically, somehow you're coming up with a representation so that each sentence, it has a linkages and it gives a probability distribution for the next one.
Right.
Each,
Right.
not just sentence, but I guess certain amount.
Not only sentence, big paragraphs. That's where transformer is unique compared to other older old school models like RNN, LSTM, and GLE. Transformer is the biggest selling point for transformer is that it can capture longer associations because it is adaptively forgetting many details in between.
But the net effect after you train the whole LLM is that you have this paragraph of words. Every such paragraph that you can think of, you get a probability distribution of the next word. That's your.
Finally, a probability distribution. But yeah. Now, for example, ChatGPT is not an LLM, by the way. It's an interface between GPT 3.5 or GPT-4 and human beings. So we have this pre-training, large amount of data, billions of parameters and so on. We have this transformer. And finally, GPT-3 if we use GPT-3, we are talking about the free version of ChatGPT, takes the outcome of the transformer and passes it through something called Instruct GPT module, which uses reinforcement learning with human feedback. Reinforcement learning with human feedback, or RLHF, continually modifies the content of the original decoder of the transformer by making it more accurate and more useful to the human beings. This is very interesting because this is one step towards removing the bias. What kind of bias I will show you now. All machine learning systems that use internet-based data are biased. What is bias? Bias means giving weightage to your favorite group. Okay. If any one of you search on Google beautiful faces, have you ever done that? Google image search, you will see 90% of the faces are female and 100% of the faces are white. Okay. No Indian. Now you see, RLHF 6 months back from now, when DALE released DALE 3, I gave this prompt to RLHF. Actually, every content you generate, it will ask for your feedback. Based on these cumulative feedbacks, it goes on, modifying the outcome of your decoder through a mathematical process. 3 friends enjoying coffee at Starbucks. I gave this prompt to DALE 3. DALE 3 is the image maker module within GPT-4. GPT-4 needs subscription, and it makes this picture. What do you 3 nice friends having coffee in Starbucks? Do you see Indians? No. Now I change and I give 3. This is 6 months back without RLHF. 3 Indian friends enjoying coffee at Starbucks. And now this is the image that they generate. So do you see now we are wearing this sort of attires in lungi and then this. This is good, but usually not seen in Starbucks. Now I think so. Continually our team gave feedback. Okay, this is bad. This is bad. This is bad. Sometimes they have spaces to write feedbacks, and based on that through RLHF. Now this is the prompt. This is the image. Now you will see on DALE 3. If you give this prompt, 3 Indian friends enjoying coffee. So do you see the difference? Okay. So GPT-4, they have amazing use cases. You can specify an app like this, and it will simply write down the app program and interface and so on. Finally, it will create a graphical user interface. Sometimes, if you give this sort of images, it can actually tell you the number of gumballs and the number of beats within each chart just from the images. These are success stories. Not only that, they will tell you how they are doing this. They will estimate the chart's volume, estimate the volume of a single beat, etc. Then divide, then find these numbers. How it does, this is the explainability interface. Then there are wonderful examples of in-context learnings, which requires very small amount of data and which doesn't require a gradient-based update of all the internal weights. So here we are talking about ICL, where you demonstrate some examples, and based on the examples, the GPT starts filling out the others. You can do long regressions by using ICL with simple LLM. Just give some examples, some part of your training data, and it will do this sort of outcomes through the model completion. Here, for example, we are changing the DDMM YYY style. This is called in-context learning, learning from very small number of examples. And then we have this sort of multimodal vision text models as GPT-4, which is very nice in explaining. So I just ask, sometimes I just look at pictures of Earth from space and I marvel how beautiful it is. Can you explain this meme? And it explains. The meme is a joke that combines 2 unrelated things, pictures of Earth from space and chicken nuggets. Now it tells you the whole story, how chicken nuggets have been arranged to look vaguely like a world map. You get my point? So this it does very ingeniously. You give it a prompt. Actually, I used this prompt when I gave a lecture on the International Women's Day at ISI. An artistic description of the panel discussion on International Women's Day, etc., like strategies for inspiring intuition, and it makes this nice, wonderful picture. But the only thing, there are some very few male characters actually in the entire picture.
None of them Indian. I said none of them Indian.
You can see on your Google, some of them can be characterized as Indians. The male characters, yeah, unfortunately, some of them are Indians. So can advanced mathematics help language modeling and betterment? We are looking at this because language models are still far away from being coping up with multilingual circumstances, free of bias, fairness, etc. And I believe many of you have heard of category theory or working with it, right? This is one very important thing coming up right from 2023 mid or so on. And I'm not mathematically formally trained in it, but we are trying to understand it for our purpose. It's a very abstract way of looking at, universes of objects which are connected through morphisms or transformable through morphisms. And as very nicely said by one of the famous category theorists, Tim Leonis, and it says that category theory takes a bird's eye view of mathematics, where the much higher from sky, the details become invisible, but nice patterns become detectable. And the idea is language is algebraic. So when we say raid and fire trap, we are just concatenating these two and creating a new phrase or a new sentence. So another word for this sort of structures is compositionality, which is the basis of all categories that we talk about usually. Language is algebraic. It is intriguing to think of what kind of mathematical tools will be at our disposal. For example, we could, for instance, revisit old ideas from abstract algebra to see if there are any new sites in the context of language and its understanding of its meaning. Okay. So an algebraist might try to formalize the FOTS code. FOTS code means a word by the company that it keeps by simply identifying the meaning of a word with something like the two-sided principal ideal associated with that word. And principal ideal, you may very well know it's a certain algebraic structure with certain kind of magnetic property. It will have a lot of its peripheral associations. And we can simply look at that entire cluster of ideals like this with what other phrases red is being used. Bright red ruby, red rover, red blooded, red fire truck, and so on. So the concept of a word like red is thus identified with the principal ideal consisting of all expressions that contain the word. But language is not only algebraic, it is also statistical. The expression red fire truck occurs much more frequently than red idea. And it also contributes to the meaning of the word red. So the probability of someone saying, I have a red idea is quite small, as the number of times the expression has been uttered is pretty low. So then hold on to our algebraic inspiration, but switch to a different set of mathematical tools like algebra mixed with statistics. How many times these are used? What are the most frequent morphisms we could have? What are the most frequent functors we could have between two categories? How one could be embedded inside other. We have these category theoretical aspects of language modeling, and you can see this extremely interesting, paper which is just there on web on the enriched category theory of language. This not only helps us to betterly model it, but maybe in future will help us to eliminate hallucinations and other
So
things.
right now, when you told us about LLM, the mental model was it's a stochastic process. We just learned the conditional probabilities.
Right.
Now, this paper, does it talk about probabilities at all or not really?
No, it is looking at language as a category, which is embeddable inside other categories, some small part of it. And it is looking at unit lemma. So it's looking at how one category could be mapped into other, etc., etc. It's a modular process. The entire back propagation. See, when we are talking about large language models, large machine learning systems, we want to know how small modules could be composed together, right? So that's where it comes. They lack the training details through which probabilities are being assigned to each of the outcomes from each layer. Now they look at how these layers could be composed together to form some meaningful thing at the final outcome, which of course is having its own value.
So is there any success story of using category theory for understanding the basic questions? For example,
back propagation, yes. Backprop is a functor. There is a very famous paper, probably in European Logic Conference 3-4 years back, that is not touched upon in these slides, but there is. And I think next year NeurIPS will see category theory workshop. for large language modeling. So something like this, let's consider a category. You know what is a category, and then language should be seen as this sort of string diagrams where you see how word is being morphed to other phrases and so on. And finally, we have the Ioneda lemma, which says that a fixed object in this category, in any category, is uniquely determined by the totality of its relationship to all other objects in the category. So, and this way, how the meaning is formed, if that is known, then can we use category theoretical principles to design, instead of using a lot of different ad hoc architectures, one principled composed architecture, which may have smaller modules inside, but give us the desired result in a much better way. Anyway, so this has just started. Category theory is very tough. People are trying to get inside of it. On the other hand, the pure mathematicians, they lack a dialogue with the machine learning people or these sort of industry people. So there is a gap which we are trying to bridge. Even in ISI, there is a big gap. When I talk to abstract algebra people, they always start with, for them, category is never related to anything that you can hold or think or smell of. They always look at it as a category of sets, category of other abstract algebraic things. But how it relates to engineering is very nice. Now in Harvard, they have started a course, Google DeepMind and Harvard. You can see cats for AI. If this type it in YouTube, you will find nice set of lectures on that. Coming to the last part, even with a shower of industrial funding, market demands lucrative jobs and media hype, are we ethically on the right track? Are we achieving equitable and responsible AI with LLMs? See, AI, the future of AI, very hard to comment for 10 years, but for 5 years, we see it is there, and it is going to be there in different strata of our social life. Theories will follow gradually. You can see for last 3-4 years, even the strictest theory journals like Annals of Statistics and Annals of Probability and TIT, all of them are publishing deep learning theory from various aspects. Okay, sometimes those theories are very useful for ourselves. But coming to modeling the bias and fairness from a theoretical standpoint, I don't think much breakthroughs are there, but it is badly needed for countries like ours. Why I will tell you. First danger sign is hallucination. Sometimes LLMs, despite their ability of in-context learning and other things, they give factual hallucination, factual fabrication kind of stuff. They can very quickly fabricate some story which was not there. User input, tell me about the first person to land on the moon itself. It's not true, actually. This is the first man on space. Translate, so instruction inconsistency. These are various types of hallucinations or errors that LLMs made out of very simple prompts. When and why, there is no characterization of that. Sometimes some specific prompts, if you make a mistake, like translate the following English question into Spanish, what is the capital of France? And it says capital of France is Paris. It was said to instruct it to translate this sentence, not to answer this question. Do you get my point? It missed that. And it answered the questions, which is certainly not required. Sometimes it can actually solve, make logical inconsistency. 2x plus 3 equal to 11, it takes x equal to 3. So when it divides both sides 2x equal to 8, it gives 3. And many times it does so. If you write the prompt in some other way, this hallucination may be removed. So we are still looking at some remedies of hallucination from an ad hoc point of view, but there is no principled reason why they hallucinate and when they will hallucinate. Then there comes the AI bots and deepfakes, which is a big danger for us. Do you recognize this baby? So it creates, and AI bots are actually, a small set of computer programs which could mimic the role of a web user, which could send tweets, which could bargain on an e-commerce website automatically, and most of them have now the interface of LLMs. Okay, this year is very remarkable because this year 64 countries are going to election, and 49% of the world population, including ours, we are going to vote. Right? We are voting actually. So, and the entire web market is full of AI bots and deepfakes. You know, our Honorable Prime Minister has repeatedly been cautioning us about those. And
I thought those are deepfakes.
But they are very dangerous in certain communities and other places, especially when you are the most coveted audience of India. But you know, common people are students of WhatsApp University, so for them, deepfake is going to be very realistic, very often. And they also create new form of gender-based violence. Women are the worst hit in Telegram-like channels. There is no regulation about that. And okay, a study says, okay, this is just some statistics that 96% of the online video contents found by Deeptrace were of intimate sexual nature, which is targeting women from common households. Jan LeCun, have you heard the name Jan LeCun? He is one of the godfathers of this. So he said 94.7% of hate speech is taken down automatically by AI. When there was this was said in 2019, when there were a lot of court cases against Facebook for communal speeches in various countries, 2019 or 20. At that time also there was a big election environment. The ground reality is that we have unfathomable training data all over the internet, but size doesn't guarantee diversity. LLMs are continually being trained on Wikipedia, PubMed. Have you heard of PubMed, this medical literature database, Wikipedia? Who are the contributors of Wikipedia and PubMed? People from US, people from Europe, people from Canada, people from Mumbai, Noida, Delhi. How many people from Tanganyika, Ghana, Nigeria, Libya, say, Lebanon, Syria, Palestine, how many people from these countries can contribute? Almost none. For them, 2 hours of electricity in a day is a very big luxury. So naturally, size doesn't guarantee diversity, first thing. And data could be static. Social views could be changing very fast. There is huge encoding bias, some examples of which I will give. There is curation, documentation, and accountability, lack of all these things in the training data. As a result, a limited set of subpopulation can continually and easily add data, share limited set of subpopulation, not the entire world, sharing their thoughts and developing platforms that are inclusive of their worldviews. This is always true. History is always the fiction of the conquerors. Nobody listens to people who got defeated, isn't it? So that is happening. And this is the training data used for LLMs. So various forms of abusive languages, not explicitly. It's not like a explicit bad name. Content filterers will suppress that. But it comes in various other indirect forms. Okay? Various forms of attacking a particular community are coming, proliferating harmful content. If you have heard of the term bias, representing a tendency of disproportionate weight against a fact person of group, there is huge amount of bias in LLMs, as you can see, because the gatekeeping is always done by those who are in power. World or society, from society we get data, data goes through AI/ML systems, then go to human review, human feedback, finally translates into actions. Every step of this flow has lots of bias, which we are now empirically looking at, categorizing, providing taxonomy. There is no theory of, or there is no underlying mathematical way of separating them out or measuring them even, or setting some parameters which could be, sensitive to such biases. For example, LLMs are used in most of the big companies like Amazon, Facebook, and others for writing performance feedback. This is the appraisal month going on. And the performance feedback when it writes, this is just a very benign example. It uses stereotypical genders. For example, kindergarten teacher, 100% it will use she. On the other hand, construction worker, 100% it will use he. Midway, you can see how it is changing. Now, this is benign, but if you look at this dialogue, what do you see? The doctor yelled at the nurse because she was late. Who was late? I was trying to take in context learning. Now, ChatGPT says, according to the sentence, the nurse was late. Okay. The nurse yelled at the doctor because she was late. Who was late? In this sentence, it is still the nurse who was late. ChatGPT will never accept that nurse, which is a hierarchically lower position, and doctor is hierarchically upper position and male, so doctor can be late. The doctor yelled at the nurse because he was late. Who was late? Now it says in this sentence, the doctor being late seems to be a mistake or typographical error. So it will never accept that the doctor can be late. Finally, after so much wrestling, it now says the nurse yelled at the doctor, she was late, who was late? Now it says the doctor. And you just ask, LLMs can be excellent coding partners. You can convert one language code to another language used just by a prompt. You just ask, give me a JSON description of the Java matching description for a person's condition to be a good scientist. It will say if the gender is male and if the race is white, then become a good scientist. Inevitable, because this bias is there, it's training data. If you look at the LGBTQ plus groups, they are extremely targeted by LLMs, and it can create several toxic prompts for this gay black person, bisexual white person, gay white person. This is how the toxicity decreases actually, coming to neutral examples. And these are some of the toxic prompts it generated without any provocation, like the gay person was known as insane and incurable, etc. A person was known for their maniacal viciousness and so on. So this is already there inside the LLMs.
So rather than calling it a bias of the LLM, we should call it the bias of society, right? It's kind of being fed upon everything that's out there.
Yeah, but
reflecting that.
if you look at the bias graph, there is
measure of it.
when it is being trained, this is encoding bias.
Yeah.
But during it's being trained, the algorithm is unable to separate it, and the human content filterers are also not separating it. So the RLHF loop is not able to separate and segregate this out. That's where it comes inside. Yeah, of course it comes from data because the society is biased.
So in a way, it's answering an important question. We want to understand how biased are we. It's a very good measure of
Yeah, we actually measure by this way. We reduce the toxicity content in steps and then try to measure how less toxic contents are being generated and so on. All these are kind of empirical. You can see more examples. This is what you are perfectly saying. This is the encoding bias. So I just say write a paragraph about my family, and it writes whenever you prompt this, it will inevitably start writing my mom is a homemaker, my father is a doctor, professor, etc. Never it will write my father cooks at kitchen and my mother is a professor. So this is a critical example of gender bias. Downstream tasks. What is the emotion captured by he loves travel alone? It predicts joy. She loves travel alone. It predicts fear. Why? Because it's a feminine gender. She is traveling alone. Fearful fact. Why? Where from it is coming? It's coming from data, and it is not filtered through the entire process. These are just bits and pieces of examples, but it is extremely there. So, the potential future challenges in the theory of Gen AI. First of all, no theoretical work exists for GAN-based translation between multiple very different spaces. For example, text to image. The basic fabric, for example, geometry of the spaces may be completely different. And text to image generation problems are partially, not text to image, but image to image problems are partially answered in one of our papers here, which uses the cycle consistency loss and develop some theory assuming Sobolev smooth discriminators and Lipschitz continuous generator functions. So we take generator and discriminator as just two functions, and then we assume Sobolev smoothness on the discriminator and some kind of other regularity assumptions, which are not extremely bad but still limiting. Exploring the thermodynamic limits to the generation process in GANs and diffusion models. Finally, you are converting noise into data. Okay. Even if you are training a discriminator, there has to be some impossibility results, which is coming from the notion of second law of thermodynamics. Very few works have tried to, address this question. Despite showing a large amount of training data, it may not generate proper content very often. Okay, why? And where it is founded, that is this impossibility result, which is still not there. Robustness in generation process of GANs and other diffusion models is a huge place. So I am showing it head and shoulder image of human beings. Some images of cats and dogs and other creatures are there in the dataset. So its generation process becomes heavily perturbed. What is the tolerance to, corrupted samples? Like in robust statistics, what we do, we try to estimate the distribution, but we can measure how will it shift if the distribution is corrupted by, outliers. Ankur Moitra is doing very good work from MIT, you probably know him, on the algorithmic robust statistics, but those works are for extremely simple and extremely lower dimensional distributions. Can we extend some of these ideas here? Theoretical backbones of transformers for sequential data is still not found. There is almost no backbone actually for sequential data. Image is fine. People are making theoretical analysis of convolutional neural networks from various perspectives. But when it comes to sequential data, which is text, almost nothing. Mathematical tools for language modeling for LLMs still immature. Can category theory help? This is a question even for all of you. Last slide. We have miles to go. Inclusiveness in training data. Understanding cultural idioms associated with different local languages. Language is related to culture. Some phrase may be very humble in my native language, very offensive in your native language, especially when we are residents of the same country. So when it comes to adopting LLM for this multilingual scenario of India, this is extremely important. Generative AI models should include a detection differentiation mechanism as a precondition for public release. This is one of the claims that now UN is receiving from scientists all over the world. Whenever a generative AI product is being launched, you have to say how you can differentiate. It's extremely difficult. ChatGPT, a paragraph generated by ChatGPT, unless you are using very stupid prompt, a paragraph, you just take a paragraph from your paper and ask it, please rephrase in nice English for an expert audience. It will write it in a very nice English. There is no way to distinguish it. That's why IEEE, Elsevier, and other publishers, they are literally begging to the authors, whenever you have something generated by ChatGPT, please declare. If you do not declare, they have nothing to do. Very difficult. Why? Because OpenAI doesn't release that. No law enforcement should be based on biased ML models, and just like VVPAT and your this electronic voting machine, any AI system for law enforcement must be publicly reviewed. Reduced carbon emission, increasing efficiency. Can we look more into neuroscience? Neural networks are extremely simple. Neural network is a dramatic term. The human nerve cells or neurons are extremely difficult, extremely more complicated. We are operating on a very naive and very simple architecture, which I was just telling Abhishek, which was conceptualized in 1950s in Stanford University, electrical engineers and some cognitive scientists. And later, after when sigmoid neural networks came, people saw that the statistics community know it 70 years back as in the form of logistic regression. But when you combine so many neurons together, neural cells or neural computational units together, what it is which is responsible for so much computation that our brain can do. Brain, if you model it like a distributed logical processor, it makes 1 exaflop calculations consuming the power of 10-watt bulb. How is it possible? We see that the neural cells are surrounded by glia or astrocytes. These astrocytes perturb the signal flow through neurons by using sodium-potassium channels. This knowledge comes from neuroscientists. Still, there is no mathematical model which could incorporate this in a regular small-scale neural network. What happens if the neural signals are sidewise perturbed by some glia-like entities? Have any one of you heard of glia or astrocyte? These are cells which are surrounding our neurons. 20 years back, neuroscientists used to feel these are insulators, which would insulate one nerve cable from another nerve cable. Now they are saying these are not insulators. They are directly affecting the flow of electric charges through the neurons by using sodium-potassium channel. That's why if sodium-potassium level is not good in your blood, our elder parents have this problem, then they start speaking, in delirium. Okay. Finally, how can we build AI technology that decentralizes power, protects our people, and offer key benefits to the most marginalized people in a community? That is the true progress. Otherwise, all these things are just very much confined to one part of the society, not to the entire population that we have. So with this, I would like to stop, and this last slide is also made by Jadavpur. Thank you very much.
So any questions?
Sorry for the study. If I show you the paragraph and I ask it, is it generated by ChatGPT? Can that question be answered by ChatGPT?
Yeah, you can ask that question. It gives its wrong answer most of the time.
It doesn't know.
It doesn't know.
So then how do we decide if we are evaluating some writer?
Some very experienced people, editors, they can see if ChatGPT has. Now we feel that ChatGPT 3.5 has special knack for special words. Like it uses the word leverage many times. Similarly, many other words. So you can look at how the words are being chosen, or what is the. And now, if you know, okay, one of your PhD scholar writes very bad English, suddenly he gives you a draft in almost fluent English. So you got to be suspicious. Okay, this is not your own. This is ChatGPT. No systematic way of
actually. If you go back to stochastic process conditional probabilities model, this is a statistical test, right? Is it coming from your output or not? It's like this is the sample coming from a probability distribution or not.
The probability distribution in statistical hypothesis testing, what you're saying, you're comparing two distributions.
Yeah.
Here the distributions are very much
so one can divide some
specified.
So one can really divide some statistical analysis.
But the prior corpus also.
In case of
already.
he has cleared about a very nice question. This is the problem for text. For image, this is what you are saying is being done.
Yeah, that makes sense.
Image is very easy to capture actually. Even from visual pattern, you can see whether it's a deep fake or not. Okay. Sometimes in images there are certain bends and certain fingers. When two people handshake, their fingers in original image and the deepfake may not be properly aligned in the deepfake. So if you are holding someone by shoulder, these fingers are not visible in the deepfake. In the original situation, they will be visible. Right. So lots of such things could be done. I don't know how many of you are familiar. I'm not showing it here. But I don't know how many of you are familiar with this one. This came to me actually for verification. So if you look at it, you know who he is? Oasis. So Oasis is standing Shiva statement. And this is actually this. So if you look at it, the hand postures, the background, etc. There are computer algorithms to capture that it is a diction.
Voice doesn't matter.
Voice will have some noise, but in case of deepfake, it is different. Deepfake different means in a normal video, whenever you are recording something, there will be some ambient noise. Now the deepfake people, they extract this audio and they remove the complete ambient noise and then they put some fabricated noise. So that is what he is saying. The fabricated noise underlying density and the ambient noise underlying density is very easy to differentiate. For text, it is not so easy because you don't have noisy words. GPT will be grammatically very correct and the words are proper synonyms.
There has been some work on watermarking as well, but I think even that is not very reliable.
It's not
Any questions? So if not, so let's thank Thomson for a very So it will be around for I think for around lunch. So yeah.
We'll get us some free lunch.
Yeah, so we now I think it's like still 5 o'clock.